Good morning everyone, I'm Dion and this is Darryl. Today we'll be presenting to you the findings of our final year project on a commercial thermal insulation coating. So firstly, these will be the contents that we'll be covering today, starting with the introduction of our project, along with some background information. Then we'll be covering on our experimental design, followed by project deliverables, results and analysis, and finally finishing off with a conclusion and reflection. So to give you a bit of an introduction on what we've been working on for the past few months, we've worked on this project in collaboration with an industry partner to evaluate the efficacy of a commercial product. So this commercial product is an existing thermal insulation coating designed to reflect the sun's UV rays for effective temperature management of the applied surface. So what we've been focusing on was inspired by a previous final year project work on other students where they made use of the LabVIEW program along with a data collection instrument that they made themselves. So however, on our end, despite going through the LabVIEW program, we couldn't get them to connect and we didn't get to make use of the instrument that they had made. So this compelled us to devise an alternative method for our data collection and storage. So our main objectives lies in setting up the experimental design to find out the heat transfer between the paint and environment, making use of our relevant coding and circuit designing skills, and then employing the properties of Excel to plot out our graphs from our findings and analyze the final set of data. So moving on, you can see here from the diagram, this is an air conditioning system, which its operational dynamics are significant in understanding the heat transfer theory required for this project. So in this process, it begins with the refrigerant fluid in a liquid state within the evaporator, which you can see on the your right hand side. As the warm air from its surroundings passes through over the coils, the fluid will absorb its heat, transforming into a low pressure gas. This then results in a cooling effect in its immediate surroundings. So now carrying the absorbed heat from earlier on, it is transported into the condenser unit over here, releasing the heat into the external environment as the fan blows over the condenser coils. So this then causes the refrigerant to condense back into its liquid state, and this now cooled fluid will return to the evaporator where the process will repeat itself. Okay, so now moving on to the background of our product. The main product we'll be testing out is this thermal insulation coating, and more properties about this paint is that it has a low heat energy transfer rate, meaning that it has a greater thermal resistance of heat transfer. This allows the pipes with the refrigerant fluid as shown before, flowing through the pipes to stay cool. So this process reduces the overall energy consumption and associated costs in cooling the fluid by minimizing the heat load on the system. And to add on to its extreme versatility, it can be applied to many different surfaces, including but not limited to building walls, water heaters, and balconies. So lastly, not to mention, it also has a high vapor permeability, meaning that it mitigates the risk of moisture building up between the coated surfaces and the paint. This ensures optimal performance in diverse settings, and particularly in the context of Singapore where the humidity levels are really high. So this is an image of the setup that our industry partners had sent us to test the paint on. And here you can see that it was initially placed in a controlled environment where it wasn't really exposed to the outside environment where temperatures may vary more. So this is why we decided to move it into the outdoors, as you can see on the right hand side, where if it rained and there were major temperature changes, it would affect what was going on in the setup. So now looking at our theory, we had to. So now looking at our theory and what we decided to, how we decided for our experiment to play out. So over here you can see the main formulas that we worked on heat transfer, and we can eventually apply them into our final observation. So with reference here to the legend, you can see that our main variable Q, which is the heat transfer rate, can be calculated by taking the change in temperature divided by the thermal resistance. And this thermal resistance can be found by taking the thermal conductivity of, by taking the thickness of the insulation material and dividing it by the thermal conductivity of the insulation layer. So now in this diagram, you can see three different scenarios that will be playing out in our experiments. So with the first one, we will calculate the value Q going through the sponge, followed by that of the paint in the second scenario. And lastly, there will be a control experiment, as you can see in the third scenario, which we will use to determine the thermal resistance and conductivity of the paint. So as you can see in the formulas here at the bottom, this one over here on my left hand side is the one that you had seen before, and with that we can translate it into a visual of an electrical circuit over here where I can represent the value of heat transfer, voltage representing the change in temperature, and lastly the resistance. So over here you can see a depiction of what the actual scenarios itself will look like. And as you can see, there are small dots on those surfaces over there, and those small dots represent where we'll be placing our sensors to record the temperature. So to prevent any risk of the refrigerant fluid leaking out of these pipes, we decided to place the sensor on the surface of the pipes itself instead of inside of the pipes to reduce any additional risks that may pose in this project. Okay, so for our second and our last experiment, you must be thinking, oh, then how will you be able to place your pin on top of the sensor itself to then place the last sensor on top, and then for the last one to place the thermal insulation on top. So what we decided to do was that after the first scenario, when we removed the sponge insulation, there was already the initial sensor that we had that we ensured to have direct contact with the pipe surface. And from there, with that sensor touching the pipe surface, we did the painting of the coating on top of it, ensuring that we painted over the temperature sensor so that we also ensured that the paint surface that was going on top of the temperature sensor was of equal thickness of the rest of the paint going around the pipe as well. So now we start to look at how we would set up our measurement instrument, since we weren't able to use the one set up by previous students. So some of our components we used were Arduino boards, resistors, relative humidity sensors, and temperature humidity sensors. So outside of this schematic, we also made use of an energy power consumption meter, and with this we would be able to test whether the different coatings on the pipe would affect the system's energy consumption. So this would then affect the overall cost of the air conditioning running system. So next we can see from this Tinkercad circuit that we used to simulate the running of our project that we then translated into the wiring on the board. So over here, this is our actual setup of how we, when we connected the temperature sensors to the breadboard itself. And you can't really tell from here, but As you can see, these yellow parts are what there are additional insulation layers that we have put on top because when these sensors came in, the wires that they had, they were stranded wires, which wouldn't really be very efficient if we were to place them into the breadboard, and the testing the results when it came out from the program, it might not have been as accurate, which is why we put into use our skills of soldering and soldered wires onto those stranded wires and then connected those solid wires into the breadboard. So now, looking at this is the Arduino code that we had programmed into our Arduino board, and our main focus over here would be in line 61, which is on your right hand side there. You can see the delay of 300,000 seconds, and why we did this was that so that there will be a delay of 5 minutes and there will be an iteration of the printed out value and readings every 5 minutes for our readings to be as accurate as possible, so that there may not be as big fluctuations if there were to be changes in the environmental temperature. So now looking at how we collected our data itself. So as you can see on the right hand side, this is not how the temperature readings are not be able to be stored in Arduino itself, as it just helps us to run the code. So we use a serial port terminal app called CodeTerm to collect, transfer, and record our data as a text document. This data in the text document is then relocated into Excel so that we can plot our graphs and compare our results.
Alright, so now what do we get from it? First and foremost, we are acquiring the data on heat energy transferred and the thermal conductivity of the insulation layers, meaning the sponge and the pane. And then, why we need this is so that using the theory, the calculations, we'll be able to determine the efficiency of the pane and to see if it's really better than the sponge or as well as the data sheet. Yeah, okay, so this shows this is the theoretical calculation of the pane. So we were given a data sheet by our data sheet partner. So in the data sheet, it already stated the thermal conductivity of the pane. So this is the heat transfer of the sponge, and this is for the theoretical calculation of the pane. So we are using this as a benchmark when we do the actual measurement using the sensors for the pane. So as you see, the pane now is very different from what the theoretical part is. So our AC system, we set at 5 different temperatures, we collected 5 different sets. First we set 70 degrees, and as you can tell, this one is in the negative zone, which is not quite optimal. It might seem optimal because we want to really see it, but this is actually the outlet pipe, which, as mentioned before in the AC system, is actually carrying in vapor. So we don't want the vapor to condense in the pipe itself, if not it will destroy the compressor when you put in. So this is not really optimal, but the other pipe is actually doing pretty good. Okay. Over here, the pane is actually doing pretty well. It's doing better than the sponge overall. So once again, for 21 degrees, it's actually doing better than the sponge. It's doing a pretty good job so far. And now when we come to 23 degrees, there's a bit more of an anomaly per se. It's not doing as good as the sponge, because this is it's allowing more heat to pass through, which is not what we want. And this is for 25 degree, our final scenario, where you can see a very drastic change, and it's allowing way too much heat to pass through. And yes, so yeah, in the earlier stages they saw for 17, 19, and 21 degrees, it was doing better than the sponge until it came to 23 and 25 degrees, where it was allowing a lot more heat to pass through than the sponge. And yeah, as I mentioned, there were some erratic movements, and all this is due to the thickness of the pane. There's something called critical thickness of insulation, which the painter didn't really reach. He only painted 5 mm of pane. Whereas over here we did a calculation. So this is a heat transfer of the pane in correlation with the thickness of the pane. So this is 5 mm, what is painted, and then this is 10, this is 10, 15 and 20. So as you see, as the thickness increases, the amount of heat passing through also increases. Not proportionally, but not directly proportional, but it does increase. And as you can see, as it gets thicker and thicker, the difference in heat transfer actually gets lesser. That is when we know that it's reaching the critical thickness. So optimally, it will be about 15 to 20 mm we would most desire. So now, this graph will show the thermal conductivity of the paint versus the sponge. So